So good afternoon, everybody, and welcome to the Future of UVEB Advanced Manufacturing Trends, Strategies, and Applications, a webinar series presented by the State University of New York College of Environmental Science and Forestry in collaboration with RadTech International North America, the Association for UV and EB Technology. My name is Brandon Murphy, and I'll be your host today here at SUNY ESF. Just a reminder that all the webinars in the RadTech series are archived at www.esf.edu/openacademy/UVEB webinar. Just quick, want to let you know that SUNY ESF has a graduate certificate in radiation curing chemistry. There are 2 online courses available spring and summer terms, an introduction to polymer coatings and radiation curing of polymer technologies. You can find out more at esf.edu/openacademy/online/RCC. I just want to do a quick reminder that the RadTech Big Ideas Conference is coming up here in March in Redondo Beach. For information and registration, you can find out more at bigideasconference.com. And with that, I am going to turn it over to our host, our MC for today, and Paul Mills.
Thank you.
You there, Paul?
Can you hear, everybody hear me okay?
Yep.
Sound good?
Yep.
Great. Well, thank you, Brandon, and thank you to everybody at SUNY ESF and to the good folks at RadTech for making these webinars possible. We're really pleased to talk to you for the next hour about transitioning to UV LED printing. I've been a part of, and maybe many of you have listened into a lot of talks about UV LED. In particular today, the perspective we have was intended to be a little bit different in tailoring this topic to transitioning to UV LED printing. You know, we thought that perhaps if you just arrived in the UV world from another planet and had no experience with UV curing, things might almost be a little bit easier. Because if you went to a place like SGIA and you walked the aisles, you'd see plenty of LED printers, run into many people who have LED light sources. You might go to ink people and see that they've developed ink sets that are customized and tailored around LED light sources. Maybe you'd bump into Jim and he'd have an LED L395 LED cure radiometer. So if you're new to UV curing, in some ways we were able to talk a new language about LEDs, about dyes and junction temperatures and, you know, very narrow bandwidths. But for many folks, they've been in, curing with UV for some time. And so they've gotten used to the technology that we've had for decades. And so for these folks, it's a little bit more difficult sometimes because LEDs represent a change. And so a new language, new equipment, new ways of doing things, and change can sometimes be difficult. So for economists, they think of the costs of changing in terms of switching costs. We have heavy investments in things that we've been doing. Psychologists know that people have to break habits. And even physicists say that we have to overcome inertia. It's tough to turn a big boat, right, from the course that it's in. So to some extent, this webinar is geared around trying to teach some new tricks to us old dogs in the industry that are used to arc lamps and microwave lamps, that have been curing with older technology, that have a 4-channel power puck and are used to measuring, their A, B, C, UVA, UVB, UVC, UVV wavelengths, and to try and talk a little bit about what's necessary to move into this world of LED curing. And to help us do that, we have 2 great speakers today. So it's me on the left, and I'm, probably know a bunch of you from much time in the UV curing world. I'm the editor of the UV LED online community, and we have 2 really, very knowledgeable folks to talk to you here. And that's John Freismuth, who's the president of Empire Screening, and then he'll be followed by Jim Raymont, the director of sales for EIT Instruments. And I thought I would just take a moment before I turn it over to John to introduce them in the order they'll be speaking. So John Freismuth is president of Empire Screen Printing Incorporated. In 1960, Empire began in a garage as a one-man operation in La Crosse, Wisconsin, and the founder, Jim Brush, named his company after what he wanted it to become, Empire Screen Printing Incorporated. And though Empire's roots are in screen printing, they've expanded into all sorts of other formats, digital and flexographic printing, to create high-quality printed products for industries like the appliance industry, automotive, aircraft, electronics, food and beverage, government work, sporting goods, and retail. John has been innovating screen printing for over 30 years, and most notably, John was one of the driving forces in LED screen printing. His lean initiatives and sustainable efforts make it possible to print with low impact on the environment. So after John talks to us about his company's experience in transitioning to UV LED, Jim Raymont's going to discuss some of the intricacies of properly measuring and maintaining an LED printing process. So Jim Raymont is the director of sales for EIT LLC. EIT was founded in 1977 and is based in Leesburg, Virginia. And they provide electronic manufacturing and engineering services to the medical, telecommunications, analytical instruments, and industrial process control customers. For industrial UV curing applications, many of you know EIT for their radiometers and for their continuous online monitoring equipment that EIT has been producing for over 30 years. EIT products provide process control to UV applications. These products can be used to establish, monitor, maintain, and control UV conditions and can assist in the design of UV systems. Jim's presented lots of seminars worldwide on UV measurement and process control. He's offered a number of technical articles and papers on UV measurement and process control, and he holds 4 patents on UV measurement. He's worked with a variety of customers in several different industries that share a common need to measure, maintain, and control UV in their process. Prior to joining EIT in 1993, Jim spent 10 years in technical sales, marketing, and management, and has 6 years as a high school science educator. He holds a BS in science education from The Ohio State University. So with that said, I will be really happy to turn over the presentation now to Jim Freismuth.
Good afternoon, everyone. My name is John Freismuth. I'm president of Empire Screen Printing. We're located in Unalaska, Wisconsin. We were established in 1960, and we moved to our current location in 1967. 19 additions, 150,000 square feet of manufacturing. We currently have right around 300 employees. We do screen printing, flexo printing, digital printing, and doming. Primary products that we would produce, aluminum nameplates, graphic overlays. So graphic overlays would be the biggest part of our business. Decals, doming, some roll-to-roll is probably the core competency of what we do. So the Empire journey started, when I started with the company, we were pretty much solvent-based company. In 1998, we looked at solvent exposure and we're looking for ways to get away from the solvent exposure on our employees. So we started transitioning into UV technology with UV mercury lamps or arc lamps, and started converting that over. In the 90s, we also started our own machine shop and building our own equipment. So we were able to make one-color screening presses. So we went from wooden tables and not a lot of ability to change the print angles or pressures, and built our own equipment at that time. And then through the 2000s, we started producing carousels, and we came across an article in one of the screen print magazines about curing with LED. So in 2008, we purchased our first LED unit. At the time, there wasn't anybody producing inks specifically for LED in the screen printing industry. So by 2016, we were 50% of what we produced LED, and as of 2018, 75% of what we produce is with LED curing, and that's all air-cooled curing as well. So when we started kind of the segments here, we got 4 different areas that we are using LED curing in the process. So the one in the left-hand corner there is a static-free belt, so we have a polymer belt. One of the nice things with LED is you don't have heat introduced into the process. So when we were manufacturing single-color presses, putting them on drying units, they were all fiberglass belts. So with the fiberglass belt, you had motion of the fiberglass belt going over the top of metal rungs and just creating static. So when we were able to use this type of belt, it took a lot of the static out of the process, and in turn took a lot of the dirt out of the process as well. So majority of our losses at the time were due to dirt. That was our #1 loss. We put in 10,000 clean room to try to prevent some of the dirt issues that we had, all controlled environments. So we had makeup air units that required us to change the air out in the building every 7 minutes. We had to convert the air out of the building. So very expensive to try to keep an environment of dirt off the material. With the LED and to be able to use polymer belts, what we found out is there isn't static on the material. So you wouldn't put a material on top of a static-filled belt, and then all the dirt in the room would want to jump onto the material. So one of the big benefits of our initial first testing was the ability to produce it without static. So then we looked at purchasing Cayman. So this was a roll-to-roll screen printing press, and so it was a 5-color roll-to-roll screen printing, laminating, splitting, die cutting, kiss cutting, finishing on the end, all LED cured. So right now we are curing that one is actually with water-based or with a chiller, and one of the lights we upgraded to an air-cooled in recent years with a little more power, and the air cool seems to be a little less intuitive on your process. So you only need the light source and an energy source to produce. Then we started building our own carousels. So we had LED, we have 3 LED carousels and 1 mercury vapor carousel. So when we started producing with mercury vapor, we started, or converting from mercury vapor to LED, we compared the energy savings. So a mercury vapor unit in our facility costs about $35,000 in energy per year to run that product, and the LED unit only required $650 a year in energy to run. Kind of the differences there with mercury vapor, you have to cool the light, so it takes the air within the building, runs it by the light, and shoots it out the top of the roof. With mercury vapor or with LED, you can use the ambient air that's in the room. And the other benefit is it's instant on, instant off. So in a 9-second print cycle, the light source is only on for just over 1 second of that 9-second print cycle. So you're looking at the difference between traditional mercury vapor and LED. Really, even when we're running it 24 hours a day, it's only on 1/9 of the time while we're running. So the huge savings there. I'll get into a little bit of the cost factors here as we go along on the actual cost of the lights. But so after we finished our small format area, we started looking at our carousel. So we had 3 M&R carousels, a 2538, 3850, and 4061. And then we purchased a 4056 and retrofitted that to LED. And we took the 3850 and we bought another 3850 Conquest, and we turned that into a 12-color LED press. So it used to be a Conquest where it would be print, and then the next station it would cure. Now every station is a print station, and we're curing in between with LED light. So that's kind of the history of from 2008 till current is where we're at with manufacturing with LED in the screen print part. So here's an example of a carousel. So same option here. The LED lights are only on during the printing process. So it prints, and then as it travels, the light comes on, the light shuts off. And we're regulating that based on when a sensor sees the table, it turns the light on, and when the table goes by, it shuts the light off. So again, it's just over a second during the print cycles. So here's kind of the where we're at with LED curing. We cure over 1,000 different substrate variations. Majority of 50% or just over 50% polycarbonate, 35% vinyls and polyesters, and 15% other. Our curing speeds are between 15 and 250 feet per minute, and all of that is UV LED and a mercury vapor formulation for our ink. So with the ink source, we're to the point now where we can cure it on either our mercury vapor line or our UV LED lines. Either area, one ink, 2 different curing sources. Major ink companies, Sun Chemical, NASDAR, were big in pushing this ahead. Ceracol, we're using Ceracol, Polymeric. There's lots of ink companies that are getting involved in looking at what this technology could be in the future. So we're curing 395 nanometers. We're using primarily 8-watt and 12-watt units. And between 5 and 7 millimeters from the surface cure. It varies a little bit on the equipment that we use for the actual curing. So our assessment of the LED part, so we have improved productivity. It increases production speeds because you don't have wait time for drying. So traditionally, screen printers would have to print, rack, or print and then wait to process orders, waiting for the heat to get out of the product. With LED, we're able to print and then manufacture the rest of the process, put adhesives on, put laminations on, die cut, and finish right in process. So it reduces the setup times as well. So with the light sources, it's instant on, instant off, so you're not waiting for the LEDs to turn on or cool down, or if you have power fluctuations, you can put the light right back on. With LED. With mercury vapor, you always have that downtime. So the improvement in registration for heat-sensitive materials, so you'd have materials that are real sensitive to heat, that don't distort during the process, or even with equipment, carousels are made of metal, so as they heat up, the registration changes. On the carousel itself, with LED, it doesn't, you don't get any heat during that process. So the equipment registers better than, as you start running, the press heats up, the register changes, you're constantly changing based on what the temperature of the actual equipment is. So improvement in reduction of static. So there's no static being introduced during our processes. The energy savings, quieter environment, so it's better for our employees. They don't have all the noise pollution that's going on. Positive impact on the environment, so no mercury, no exhaust, and no ozone emission. There are some challenges when you're dealing with LED curing. Sometimes we have to slow the line speeds down for cure. And a lot of this was during the development stage. From 2008 until 2018, the technology's come a long way. But there still is some instances where certain materials you might have to slow down for the curing. In some colors, we've experienced yellowing during the curing process, especially in blues and grays, and also in silver backgrounds. So what we have to do is we have to change our process. We have to check the inks wet, so we actually color match prior to curing. If we have a good color match, then we're curing with that color match. Otherwise, you're having to wait 25 to 30 minutes for the color to come back to what it would be. So it's a little bit of inconvenience in the process for that. And there still isn't, for 10 to 15 or 5 to 10% of the inks, we can't run LED for certain substrates. There's not another option for us to be able to do that. So we're still have some mercury vapor options, but our goal is to someday, hopefully in the next 10 years, to be able to be 100% using LED technology. So some of the transitioning being first, testing. So we started out with LED. We didn't have any options. Nobody had any ink, so I started calling ink companies. Our major ink company was actually told me that the polymer or the photo initiator that was in the ink that we had now would cure at 395. So we tested that theory and we got cure at 5 feet a minute. 5 feet a minute wasn't really an option, and we didn't get really good surface cure in the inks. So in our early stages of testing, we ended up having to add heat prior to the cure. So we'd have to print it and then heat it up with a heat lamp and then cure it, and still the speeds were slow. There was only one ink company working, and that was, so the ink company that we had initially was working on a different environmental process of putting vegetable oil in their ink. So they weren't really in a position to start testing. So we started looking at other ink companies, and NASDAR stepped forward, could see the vision of what this ink could be, and started developing inks for LED, which we were able to get to the point where we didn't need heat. Curing speeds got fast enough to where we could run manufacturing or production, because in the beginning the speeds are way too slow for the actual production. And so the cost was a little more as well. We paid about 30% more for the ink than we would have running mercury vapor, but all the inherent benefits seemed to outweigh that. Rematching of the inks, so we had to match different inks for different substrates, so there was a big investment in rematching inks at the onset. The two inks, so we had one ink for mercury vapor, we had one ink for LED. So there's still that cost of maintaining two different ink systems in the beginning. The light curing sources were only 4 watt, was the highest they had when we started. And no one made any LED printing equipment or curing equipment. So we had to produce our own equipment or make our own equipment. So we could buy the light source, but then we had to manufacture equipment to build our own light sources. So we were somewhere in the cost of producing per inch for curing about $2,500 an inch. So today, if you were to transition, a big part for you guys would be that you'd have to test that it works in your own process. Rematching of the inks, but Now they have inks for both mercury vapor and LED, so one ink that would cure in either. There still is a higher cost, but as more people develop their LED technology and get involved, economies of scale should drive down the cost of the inks. It isn't so much that the pigment costs more, it's the volume of how many people are buying it. The light sources, we've tested between 8 and 16 watt. We don't feel we need any more than the 12 watt cure to run within the process that we have. You can buy rubber belts to eliminate static, carousels as well. So if you have processes where you're curing on a carousel, you put material on a solid state and it eliminates the static. No racking, no wait times. And I think that's probably the biggest issue is the wait times, is printing all the product and let it sit for 24 hours before you can manufacture it. Here, you can manufacture right to the end. Cost is about $1,600 an inch. I'm going to show you a couple videos. The first one will be of the Cayman press. So, Brandon, if you could run that, that'd be great. All right, so that's an example of a Cayman roll-to-roll screen printing. So we've been running that since 2011 in manufacturing every day. And on the second video is going to be, I'm going to show you the cellular manufacturing. And then I'll talk a little bit after the video of the benefits of the cellular manufacturing with LED. So Brandon, if you could play that. All right, so that was cellular manufacturing. All the videos on our website at empirescreen.com has a how-to section. So if anybody wants access to them videos, they are on our website. The big benefit when we've seen LED technology was partly that we were able to produce without solvent exposure for our employees, but there was a huge financial benefit. We were able to manufacture the process in a cell, so we could go from raw material to finished product, which was huge for our turnarounds. You know, when I started, you'd have a process with, we'd screen it, then we'd laminate it, then we'd split it, then we'd die cut it. That process would take 14 different supervisors QCing it through the process. Now if we produce it all in one format, 4 people are responsible for it from start to finish. So the quality gets built in by the people. If you have an issue, you can correct the issue why it happens. With the LED curing, there's nothing stopping you from manufacturing raw material finished product. So that's kind of what I had for a presentation. We'll take questions at the end after Jim talks. So thank you, everybody, and I look forward to the question and answers at the end.
Well, thank you so much, John. I think the industry owes a lot of gratitude to John and to Empire, not only for sort of going through the school of hard knocks and paving the way for others, but also John's really been very open and transparent about what's happening at Empire. I mean, he's literally opened his doors to the industry to come in and see the success and the challenges that they faced and how they overcame them. So we appreciate that. I'm sure John would tell you, and Jim knows, that after putting that equipment in and transitioning to the process, the work isn't over yet. And so Jim's going to talk a little bit about maintaining and monitoring the UV curing process.
Thanks, Paul. Thanks, John. EIT is a contract manufacturer, and we got involved with UV curing instruments because we had some boards back in 1984 that weren't cured properly, and we thought there had to be a better way to do things. Our main business is contract manufacturing, as Paul mentioned. Our most visible business right now are our UV radiometers. We do not sell any sources. We don't sell inks. There is a wide variety of UV LED sources available, and the suppliers then have a wide level of technical expertise. I think you need to take advantage of those suppliers and their expertise. As John mentioned, you do have to match that source to your application. You really have to look at the different suppliers for their stability, support, and financial resources. The old song there, I think it was by Carole King, "Will You Still Love Me Tomorrow?" I think that's really appropriate here with UV LEDs. Will the LED company that you buy from, will they be around tomorrow? Will they be able to support you tomorrow? If you buy a particular instrument today and you need to replace it 5, 6, 7 years down the road, will they have a drop-in replacement available for you? So this is something that you really have to look at when you're researching which LED company to use. And then, as John mentioned, the economics have gotten better over the years. He was a pioneer. I think that this is another thing that you're going to have to evaluate for it to make economic sense. The reasons why we want to measure LEDs are really the same reasons as why we want to measure broadband sources. Number one reason there is we should be able to save you time and money when you're using LEDs if you're able to control the process. The other things that are listed there, to establish a process window, drive your maintenance, all of those different things are important, but the bottom line is we have to be able to save you time and save you money with measurement. When you look at LEDs, the first thing you'll say, well, they're very stable. The source is stable for many thousands of hours. Why would I want to measure it? Well, you have the coatings. That's going to be the first thing there. And then you also have your substrate. All three of these different areas, the source, the coatings, and the substrate, have to play together. There's a number of process variables here that are going to be adjusted by humans or maybe not adjusted by humans. There can be things that could possibly fail. We've had instances of people putting the wrong LED on. And then you also then want to look at any of the particular failure modes that may happen or things that weren't adjusted. This is the reasons why you want to measure LEDs and the LED process. If Voltaire was around today, he may change the saying here that common sense is not so common to UV common sense is not so common. Those of us that have been in the industry for a long time see this. I've just come back from extended travel. One of the things that I saw on the recent trip here is the customer did not verify their source type. They thought they had an LED that they were working, wondering why the instrument did not measure properly. They actually had a broadband instrument, or broadband source, I should say. It wasn't matched. The instrument was not matched to the source type. You've also got to match the instrument, the band that you need, to the right source that you have, and also the right dynamic range. You can also run into an example here with formulation. It's got to be matched. I was at a medical manufacturer that was relying on short wavelength UVC to produce their product. A very narrow UVC process window in order to produce this. Their hands were really tied because they could not change the formulation for this particular product without going back to the FDA for approval. It's not very realistic to expect that they will get the same results by taking out that short wavelength UVC and plugging in a 365 nanometer LED. So this is something here that you just can't take one off and necessarily take the broadband shortwave source off and put the LED on without doing the proper research. I think this particular company really underestimated the effort that was going to be required. Their hands were tied. They couldn't look at different types of formulations without a wide implication with their product. We also run into examples when people are not all that smart or don't have much common sense when it comes to measurement. This is a particular customer here that measured their LED in August. They measured again in January. Their first assumption here when they had the drop in both the watts and the joules was that the instrument had gone bad. After much back and forth, it came back to us. We evaluated it. The instrument was very close to the original settings. We made an adjustment of less than 2%, sent it back to the customer, and in February they got the same readings as they did in January. Quite a bit of back and forth on the phone, and again, this was a very smart group of researchers. Looked at the data, went back and forth over the course of an hour. We went back to one of our original suggestions, and they did check the LED, and there was ink coated on the LED window. A lot of times there are very close tolerances. The LED is close to the substrate, so this is something that you do have to check. This is something that you may have to look at from a process control situation. As LEDs get a little bit more powerful, a lot of folks can back off a little bit, but that still doesn't mean you have to check. Instead of cleaning reflectors that you may have on a broadband source, you may have to check the quartz window on the LED. Want to make sure when we're working with LEDs that we're still speaking the same language, the irradiance or intensity. This is going to control the depth of your penetration through pigments or opaque colors, and also your adhesion to the substrate. We also talk about the dose or the radiant energy density. This is going to be inversely proportional to the line speed. Oftentimes, this is the only UV exposure guide number supplied, but I think it's a combination of both joules and watts to get that process window that you need. When you look at the watts and joules, a lot of the instruments will have the joules and the watts listed. In this particular case, we've been under two different LEDs. You can see the band, you can see the joules, you can see the watts, and how many times you've been underneath that lamp. LEDs are usually sold by the nanometer wavelength. It's a center wavelength. Common sources run from 365 to 405. The center wavelength, if you're buying a 365 nanometer lamp, the center wavelength can be sold as plus or minus 5 nanometers. This has to do with the binning of the source. So the center wavelength could be anywhere from 360 to 365 to 370. You do have to match that to your formulation. Other thing to note with LEDs, with broadband sources, we typically have an inverse square law. Go twice as far away, I have 1/4 the intensity. That's not always true with LEDs based on how they're put in the array. So this is something that you're going to have to look at and understand if you decide to back that LED array up away from the substrate. So proper curing requires a combination of right wavelength, right watts, and right joules. These are the things that we like to see as you do your process window. The other thing that I'd like to point out, so often LED manufacturers want to impress you with how many watts that they have. This is not always the most important thing. With a higher watt LED array, you may be able to turn the power down. You may be able to move that LED array a little bit further away from the cure surface, but you can't judge an LED array only on the watt output. There's been some research here lately that joules are just as important, and how that LED energy is delivered is going to help with the polymerization. So these are all things that you have to look at, not just the sheer watts, but the joules and how that energy is delivered. You look at a broadband source, you can see that it is spread here. There's a couple different sources here, mercury, gallium, iron. You look at just the rectangle here, this is going to be the area of a 395 LED. It is going to be a concentrated area, not necessarily a single nanometer of energy, but it is going to be an area that's much smaller. It's not a broadband source like a mercury arc or mercury microwave type of lamp. If you take a standard instrument, one that's designed for a broadband source, in this case it's a UVA bandwidth response, and measure a 395 source here, you can see that we're going to be about 95% low on this here in terms of the number. You can also see here, if you measure a 385 source, we maybe underreport that source by about 60%. Based on where the LED falls on this curve here, if you've got 380 versus 385 versus 390, that can vary quite a bit for a 385 source, or if you've got 390, 395, or 400 with a source, that's also going to impact exactly how low or how much you underreport that particular source. So you will get a number with a standard source. We looked at several LEDs, and things that we found, that we looked at the width of the LED at the 50% power point. It can run 20, 25, 30 nanometers, and that's going to vary based on the suppliers, based on the binning, based on a lot of suppliers will have longer wavelengths in there versus shorter wavelengths. So a 395 LED output may tend to be a little bit higher than 395 versus shorter. You can also see that most manufacturers are going to sell these as plus or minus 5 nanometers, and that would be perfectly acceptable based on their tolerances. But if you're going to define the right band, you have to look at something, in this case for a 395 source, it's got to include and measure the energy from a 390 to you've got a 395 source right here, you've got a 390, 395, 400 nanometer source, and you want to be able to include that in the total response. The other thing to look at when you look at a radiometer, radiometers are composed of different optical components, and with this here we try and take those optical components here and put that into the height of the instrument. Traditionally, broadband radiometers have only been defined by their optical filters. So the response of the instrument is based on that optical filter. So the responses that you see here for a broadband radiometer are going to be based just on the optical filter. What we did is we looked at all of the different optics in there that combine in that stack and looked to find a way to include those in the response also. So each component has its own response. When you look at different things there, what we want to try and do is put all of these together and also include any of the energy that may come at an angle. It does have a tendency to change the filter response, energy that may be at a low angle, and put all of these together here into an instrument response. And this is something that we've done with our patented total measure optical response. In this case here, we have a response here that is at 370 at the 50% power point right here. And then I also then have it up to 422 at the 50% power point on the long side. So what you'll have then with a 395 source will be able to capture almost all of that energy except for 1 or 2%. We also looked at how do we improve that calibration process. If industrial sources are now pushing 50 watts in the lab, and if we look at NIST that's used to running much lower irradiance levels here, how do we reduce that error process during the calibration process here? One of the things we did is have our master radiometer evaluated by NIST. The other thing is we found through our research here, there's a number of sources on the market that do very, very well for curing of chemistry, but we want something that's a little bit more uniform in order to use this as a calibration source. So a lot of our work has been done to evaluate calibration sources to get one that's very uniform. We've also worked to develop fixtures here where we line things up. So we put the unit under test as well as our master unit into the LED source in the same place each time for complete repeatability and also stability. If you have an instrument wish list for process control, you're going to want it portable, flexible, a high enough dynamic range. You want to be able to account for that natural variation. You want to be able to use it both in the lab and in production. Affordable. You also want good performance. We talk about unit-to-unit performance. We're talking about two different instruments there. We talk about source-to-source when you have one instrument and two LEDs. We also talk about the performance of one instrument run-to-run. We also want good accuracy to a standard. So this is some information that's been collected not by EIT but other LED manufacturers. They looked at some of our products here. In this particular case, we have very good accuracy in terms of the watts. They tested, Phosion in this case tested a 16-watt source, and we tracked very well with another NIST traceable radiometer. When we look at the energy density or the joules, the calculated value here is over in the right here. And then we also have the value that we delivered, and it's a little bit better than some of the other products there on the market. But having the correct number of joules is an important parameter. We also have good linearity. This is measured by Phosion. And then we also had good accuracy when you look at it compared to some testing done by Excellitis to the national standard that they have up in their facility outside of Toronto. Additional testing has been done by others, so it's repeatable, it's accurate. We also look at this testing that's done at EIT. I would point out that the Y scale here is a total of 1%. When we look at 20 different runs here, from 1 to 20, we see the natural variation between the LED. But when we look at this little gray line here, the instruments match each other within 0.2%. So we're getting very good performance unit to unit. The LED cure is available where you can get the numbers on the display. You can also download this here to a computer here, so you can look at things like height level changes, and then you can also look at power level changes. So in summary, you have to have some common sense when you're measuring LEDs. LEDs are stable, but there's process variables that we need to be able to track. You need to have the proper instrument. You will get a number with a broadband instrument, but most likely it'll underreport. There are instruments available that do a very good job of measuring LEDs. You have to be able to utilize the resources here on webinars like this, and also LED source suppliers, formulators, measurement folks, and also end user resources like Empire Screen. With LEDs, for me, it's really been something learning every day from our customers and from other people in the supply chain. RadTech does have a seminar that will be at SGIA for anybody who will be there. It'll be Friday, October 9th in the afternoon. And then Brandon also mentioned then that we have the event next March out in Redondo Beach. But, that's what I have there. I think, Brandon, you can take it over then.
Hi, Jim. Yeah, it's Paul. Thank you so much for all of that good information, both about how people have to think about both the instrument that they use and the procedures that they're going to use. So, again, this idea of transitioning requires some rethinking about these things, and EIT's done a great job of figuring that out from the measurement standpoint. So we're going to try now to take some questions and answers from you. You should be able now to type into the window questions that you may have. You'll notice that on this slide we also have given you each presenter's email address. So if you need to go, or if you have a question that you didn't want to ask in public but you want to send to either John or Jim, you've got their email address here, and I'm sure RadTech would make that available to you as well after the webinar. In fact, my understanding is that this webinar will be archived and available to you after the webinar. We scheduled the webinar to go to 3 o'clock, so we have some time, but the speakers agreed to stick around a little bit longer if we get a bunch of questions and folks want to hang on for a few more minutes. So I thought we'd start off with a question from Rustrum, who says, are there UVC LEDs for surface cure? Anybody want to tackle that question?
This is Jim. There are UVC LED cures available. I think, at least to my understanding, there's quite a bit of people working on it. The intensity levels are coming up. The costs are coming down. They're working on the lifetime. The last I heard from a recent trip and talking to a chip manufacturer, they feel they're still 2 to 3 years away until they're economically viable. But there are folks working on things, and I think this is something that you really have to track almost every day.
Yeah, Jim, I also know there's a tremendous amount of activity that RadTech is involved with outside of curing processes, like health applications, where shorter wavelengths that are used in disinfection are being heavily worked on, and RadTech, of course, works with the organization UVEB in those areas. So you might want to check out, Rustrum, the work that's going on in these shorter wavelengths about what's going on in germicidal and disinfection applications as well, because they're doing a lot of work in short wavelength UV.
And the other thing I would add, you may not have these at 254. You may see some of these up at 275, 285, or somewhere in that region. And right now, the last I heard, we're getting 40 to 50 milliwatts of output. There may be more as things have changed.
Great. So RJS, John, you mentioned that 5 to 10% of inks are not LED curable. What are those inks, and why can they not be cured?
That was more of a reference to 5% of the substrates that we print on don't have an ink yet for them. So it's not that if they don't have the right photo initiator to cure with LED, and nobody's making one yet for that range. So it's more about 5 to 10% of our substrates don't have an LED ink being made for it yet.
Great. John, we also have a comment from Leon who says that he's learning to work with UV LED, and for him, static is very important. Any comments about static?
Yeah, I think that was like one of the biggest, you don't know what you don't know until you start running LED, is that we were able to use a different belt and cure the material under a belt that didn't create static. So we found out if you can get rid of the static in the process, there was a huge benefit on the backside of that. So when you're curing,
Jim,
go ahead.
No, go ahead.
So I'm just saying, like, all of our curing prior to that was using a fiberglass belt running over the top of metal. So it created the static right in the process that we were producing on. So No matter what we did prior to putting it on the belt and curing it, once you put it there, static was created and dirt was attracted to the material. So having an option to where you can get a belt because the heat isn't there, that won't create static is a huge improvement to the process.
Excellent. Jim, Amy wants to know if there's any work underway to create an LED version of the micro-cure radiometer.
It is on our roadmap. There's several things that we're looking at here at EIT. Will we have it tomorrow? No. There are some challenges to get something that's only 1/4 of an inch high.
And I guess, Jim, that ties into Brian's question, which is if the curing distance is so short with LED, 5 to 7 millimeters, how can you fit a power map under the lamp?
A lot of the instruments are 0.5 inches high. A lot of times you can raise that LED up in order to get the instrument underneath there. Sometimes folks will take this off and put it on a measurement fixture, but you do want to try and replicate that. There's other folks that will sometimes put the instrument in the park position of a digital printer and bring that over and be able to adjust the substrate height that way.
Mm-hmm. So also, Jim, Punit wants to know, do you have a puck or some instrument that they can use to measure UV LED curable ink that's printed on a cylindrical container, so something more three-dimensional?
At this time, we do not. There are options in terms of relative measurements with sensors, things like that, but not anything that could fit through the cylindrical container, such as a yogurt cup or something like that.
Great, thank you. So, John, Eugene wants to know whether something about the average lifetime. How do you talk about lifetime of LEDs and whether on-off cycling affects their lifetime?
I'm not an expert in the light technology itself, but from our supplier, there is no effect for instant on, instant off. They guarantee 5,000 hours of continuous use, so with no degradation, turning it on, turning it off. So we're looking at one light source being able to last the way we manufacture, and we run 24 hours a day, 5 days a week. The light's lasting 30 years. So we haven't had failure, and we've been running lights since 2008. So we're 10 years in with any issues. So.
Sure, and that's been my experience, Eugene, which is a lot of the light source manufacturers have had difficulty actually calculating or empirically testing the lifetime of the LED source because they continue to run up until there's new sources that sort of obsolete the old sources. I think some work also needs to be done on talking about what does that mean? What is the lifetime value? Because unlike the failure mode of an arc lamp or a microwave lamp, LED arrays are built out of individual dies, and sometimes it's a die or a row or a column of dies that might fail and not the entire source. So, good question. We have a question from Zach. Why did blue and gray pigments yellow under LED?
Again, I'm not the expert in the ink series, so from our suppliers, the photo initiators and some of that ink development was causing it to yellow, but it was temporary. It always came back to the original color, usually took less than 30 minutes.
Excellent. Jim, the question about how do people, sort of a combined question, how often do I need to measure my process and how do I care for a UV measurement instrument?
I guess the first question, how often do you have to measure? It really depends on your process. I always tell folks to measure more often, and if they have to, back off. It's one thing, I guess, if you're screen printing signs. It's another if you're using LED to make heart catheters. I always tell folks I may need one of those heart catheters someday, so it's probably good that you measure more often if it's something more critical like a medical product. The biggest thing with care of instruments is to make sure you treat the optics like optics. We try and make instruments durable, but they're not infallible. So whether it's our instrument or another product, follow the manufacturer's recommendations for what you can use to clean it. And keep in mind that anything on those optics can impact the readings up or down, as well as things like coding.
Great. How about you, John? Any comment on that?
Yeah, we test weekly, so we're testing the lights weekly, but we also do a crosshatch test on every single job we run, and then if there's an issue with curing on anything, then we test the lights if there's anything during the crosshatch test.
Jim, a question from Bill who wants to know, I've seen that there are profiling radiometers. How are these different, and what are the advantages?
The profiling radiometer in most cases performs just as a standard radiometer and has the added feature then to be able to download the irradiance profile to computer. The irradiance profile is a function of the watts versus time. With this, you can track things such as power levels. You can compare brand X to brand Y in terms of how that energy is distributed. You can also then look at October versus September values. And then also, if you're in the supply chain, if you set things up and everything's working, for example, if you're an ink manufacturer, you measure that, and your customers has everything curing, you have a record of that. You can go back if you get a call that things aren't curing and help them get back on track then very easily by seeing the differences with that irradiance profile versus just a number, or two numbers, I should say, joules and watts.
Excellent. John, Zach would like to know, what is the maximum coating thickness that Empire can cure by LED?
I don't have the exact answer to that. There is no difference between mercury vapor and LED. We're using 390 mesh coated 1 or 2 and 2 for our standard UV, and it doesn't change. But I don't know what the exact thickness coating would be.
Sure. We'll see if either of you can comment on this. And again, it's more of a lamp type question, but Punit wants to know about the difference between air-cooled and water-cooled LED units. What are maybe some of the advantages and disadvantages of either cooling approach?
For an operation standpoint, the air or cooled air is in our building. It doesn't cost anymore. To put a chiller unit in or a water unit in, it would be an added cost. So with the air cooled and the whisper drives, they're pretty good for, and like I said, we haven't had failure in 10 years. So it might be a little bit how you're going to use it. So with us having instant on, instant off, and only running it 1 second during a 9-second print cycle, we don't worry a lot about the light heating up to a point where air cool wouldn't be an efficient form for us. Originally, we started with water cooled on the Cayman because that was continuous use. So I think some of it would be the environment. If you're putting it in an environment that isn't cooled or isn't air conditioned or room temperature, you might want to look for a different cooling source.
I think it's something that you work with your source supplier to find out what's best for your particular application, whether it's air-cooled or water-cooled.
Excellent. Well, I want to thank both of our speakers today, and once again also Brandon behind the scenes making this all possible. You have the email addresses for John and Jim, so if you had a question that you wanted to ask offline, please email them. They'd be happy to work with you. Thank you very much for attending this webinar, and again, it'll be archived so that you can share it with colleagues in the future. Thank you very much for tuning in today. We'll see you soon.
Thanks, everybody. Have a good afternoon.